Welcome to The Explainer. Today, we are diving deep into a really critical concept for any large-scale system, consistent hashing. We're pulling this straight from Chapter 5 of that must-have book, System Design Interview by Alex Hu. So, let's get right into it.
Okay, so let's set the stage. Imagine you're running a huge service. You've got millions of users. Now, servers are going to fail. That's just a fact of life. And you're definitely going to need to add more servers to keep up with growth. So the real question, the big one, is this. How do you handle all that change without the entire system just collapsing? That's the core problem we're going to solve today.
Now, before we get to the really elegant solution, we've got to understand the problem. And to do that, we need to look at this simple, common-sense approach and see exactly why it just completely falls apart when you try to scale up. This is what's known as the rehashing problem. So, a super common way to spread data out is with a really simple formula. Let's say we have 4 servers. You just use hash %4. What this means is you take a key, you hash it, and whatever the remainder is, well, that tells you which server gets the data. So key 0, it lands on server 1. Key 1 goes to server 0. And you just do that for all your keys. Simple, right?
And you know what? As long as nothing ever changes, this works great. It's beautiful, actually. Every server gets a pretty even slice of the data, the load is balanced, everything's humming along just fine. It's simple, and it works. But here's where things get messy. Because the real world isn't static, right? Servers fail. So what happens to our perfect little formula when n, our number of servers, suddenly drops from 4 down to 3? Total chaos. That's what happens. The formula now becomes hash %3, and just look at the result. It's a disaster. Almost every single key now maps to a totally different server. It's not just the data from the one failed server that has to move. It's practically everything. If this were a cache, you'd trigger a massive storm of cache misses and probably overload your entire database. It's a system-wide meltdown.
Okay, so that simple modulo approach, it's way too brittle. It can't handle a dynamic system. We need something better, a way to add or remove servers that doesn't cause this complete catastrophe. And this is where our hero, consistent hashing, makes its grand entrance.
The formal definition really tells the whole story. It's a hashing method designed from the ground up to minimize disruption. When the number of servers changes, only a tiny, proportional fraction of keys actually have to move. This is the stability we've been looking for.
So let's see how this actually works, because it's a really cool idea. First, you need to forget about thinking of your servers as a simple list from 0 to n. Instead, I want you to imagine the entire range of possible hash values, but wrapped around in a circle. We call this the hash ring.
Now, here's the clever part. We take our servers, S0, S1, S2, and S3, and we use the same hash function to place them on the ring. So their position isn't some arbitrary number. It's determined by the hash function of something unique, like their IP address. And here is where the magic happens. To find out where a piece of data should live, you hash its key. That gives you a point on the ring. Then all you do is travel clockwise from that point until you hit the very first server you see. That's its home. So in our example, key 0 travels clockwise and hits S0. Key 1 keeps going and lands on S1. This simple clockwise rule is the heart of the whole thing.
Okay, so we've got this new, elegant system, but does it actually solve our original, catastrophic problem? Let's put it to the test. Let's run that exact same failure scenario that caused a meltdown before and see what happens now.
And here it is. This is the payoff. Look what happens when we pull server S1 out of the ring. The only key that has to move is K1. Why? Because S1 was its home. So now K1 just continues its clockwise journey and finds its new home on S2. Every other key, K0, K2, K3, they don't move. They don't even notice. The disruption is surgically contained. It's beautiful.
And it works just as gracefully when you add a server. Let's say we bring a new server, S4, online. We hash it, and it lands on the ring. It now becomes the new home for any keys that land in the space just before it. So in this case, it takes ownership of key K0 from server S0. And again, the impact is tiny, it's localized, and the whole system just scales smoothly.
So this is a huge improvement, right? But there is one more potential snag. What happens if, just by random chance, our server hashes don't spread out nicely on the ring?
Exactly. I mean, it's totally possible that a few servers could get hashed to positions right next to each other, while another server ends up all by itself, responsible for this huge chunk of the ring. That would create a really unbalanced load. You'd have one server getting totally slammed with traffic while the others are just sitting there, bored. We call that a hotspot, and it's a big problem.
To solve this distribution problem, we introduce one last really clever trick. It's called virtual nodes, and this is what makes consistent hashing truly battle-tested for the real world. So instead of putting each physical server on the ring just once, we represent it multiple times. For example, the real server S0 might appear on the ring as a bunch of virtual nodes, S0_0, S0_1, S0_2, and so on. We do the same for S1. What this does is it effectively chops the ring up into way more, much smaller pieces. This averages everything out and makes it incredibly likely that each physical server ends up with a fair share of the load.
Okay, let's zoom out for a second. We've gone from a system that breaks easily to one that's super resilient, and we've even tweaked it for better balance. So, what's the big takeaway here? Why is this one of the most important ideas in all of distributed systems?
Well, the benefits are just massive. First, and most importantly, you get almost no data reshuffling when servers come and go. That makes horizontal scaling, just throwing more machines at a problem, incredibly simple and safe. And like we just saw with virtual nodes, you get a much more even distribution of data, which is how you get rid of those nasty server overloading hotspots.
And I want to be clear, this is not just some academic theory. This is the real deal technology that powers some of the absolute biggest services you use every single day. We're talking about Amazon's DynamoDB, the database Cassandra, Discord's entire chat platform, the CDNs that deliver content to you, even Google's core load balancers. They all depend on consistent hashing to work at a planetary scale.
So the main thing to take away from all this is that consistent hashing isn't just for one thing. It's a fundamental pattern for distributing anything, whether it's data, user requests, or background jobs, in a way that can scale gracefully. So the question I want to leave you with is, now that you can see this elegant pattern, where else do you think you could apply it?
Hey, if you found this breakdown useful, it would be awesome if you'd hit that like button and subscribe to the channel for more deep dives into system design. Thanks so much for watching.